Good morning, Ray. Welcome to this interview. It's a great pleasure to spend time with you. Good morning.
Good morning, thank you.
So when I was a graduate student, I was very fortunate to have your book just came out. I think it was in the late 80s, let's say. And I think it was a very important milestone for me to have something in my hands, and I could learn energy loss spectroscopy. So I thought, at this stage, after many years, I thought it would be interesting to know a bit more about you. So I wanted to ask you some questions. So when you were a young boy, what drew you to science? I think that's interesting to see how you came about to energy loss spectroscopy. So going way back, can you tell us about how you got into science?
Well, starting with school days, you probably don't know the educational system in Britain in the 1950s, right? There was an 11 plus exam that selected 20% of the population for an academic education. So they went to a grammar school and the remaining 80% went to a secondary modern school. And so I took this exam at age 11 and I thought I didn't do very well, but managed to pass. And in those days, there was no political correctness. And so the morning after the results had arrived by mail, the teacher said, all those students who passed the 11 plus exam, raise your hand. And I was sitting near the front of the class, and I remember the teacher's look of surprise when he saw that I'd passed the exam. So I ended up going to Stretford Grammar School. And there I found that there was homework and that there were real consequences for being lazy, writing lines, extra work, that kind of thing. So with these incentives, I started to do fairly well in all the courses, I think. And then after 2 years, the school separated the stream into 3 parts. There were people who were going to study many arts and study Latin, which was supposed to be good for the mind. There were people who were going to specialize in science and study German, which was the language of science, thought to be. And then there were people who were just going to carry on without any Latin or German. So somebody decided at that stage that I ought to concentrate on science. On what basis, I don't know. But that I did for the next 5 years or so, and eventually took scholarship exams and got accepted by the University of Cambridge for the natural sciences tripos. And that included physics and chemistry. And at that stage, I hadn't decided whether I wanted to do physics or chemistry. So some advisor said, you should start off with organic chemistry, which is only offered every second year. And so I ended up spending 3 afternoons every week brewing up various chemical compounds in the labs in Lensfield Road in Cambridge. And then after 1 year at Cambridge, as you probably know, there is a preliminary exam, which doesn't count towards the final degree, but is a means of assessing performance. And in my chemistry exam, I messed up and answered all the wrong questions. They had used the same exam paper for 3 groups of students, and you had to answer questions in different sections of the paper. And so as a result of that, I got a rather poor mark in chemistry, and I was summoned by Professor Sir Lord Todd, who was the head of the chemistry department there. And he told me I would not be taking any more chemistry courses. And I think I didn't think to question at the time to explain why the mark was poor, but at least I'd answered the question, should I do physics or chemistry? So I ended up taking physics courses at the Cavendish Lab. And I found some of those fairly theoretical. And I heard then that the engineering department offered a course called Electrical Sciences Tripos, EST. And so I ended up spending the final year at Cambridge doing EST with lectures from engineers that I enjoyed much more, and practical classes. I was interested in electronics, that kind of thing. And in the engineering department at Cambridge at that time, they were developing the scanning electron microscope. Charles Oakley was the head of the department. Bill Nixon was there, Grigson. And I probably could have stayed in Cambridge to do a PhD, but they were not willing to guarantee this until the results of the Part 2 exam were known. Whereas Imperial College in London was willing to accept me without any conditions. And I rather liked the idea. I ended up living in the center of London for 2 years, where you could walk to the theater and to concerts and all this kind of thing. So I enrolled at Imperial College in the electrical engineering department. And on the 7th floor, they had a materials section, work on different properties of materials. And they also offered a materials science MSc course, probably one of the first in the UK, at least. And there were lectures there given by people from different departments. And I remember, for example, a chemical engineer taught thermodynamics. And so I saw there the same equations that I'd seen in Cambridge, but this time the engineers put numbers into the equations and units. There were units and numbers, and that seemed to suit me. And still to this day, I think I have a preference for publications that present results in numbers or graphs, and not just relative units, but actual units, centimeters, seconds, whatever. And so that probably has influenced my approach to science. It's more an engineering kind of approach.
Did you?
But in Imperial College, that's how I got into electron microscopy, actually. I had a project, I was given a project involving epitaxial films of semiconductors, lead telluride, and so on. And besides electrical measurements, I was allowed to use the electron microscope, which was a GEM 7, 60 kilovolt, I think, kept in a locked room with a special key. And I was one of the few people allowed to use that microscope. And I used it to study the nucleation and growth process of thin films by looking at the edge of the film, where the thickness goes down from a few thousand angstrom units down to 0. And in that small region of the sample, you could see the whole growth sequence of the films, rather like seeing the whole of human evolution in the embryo over 9 months. So that impressed me, that in a single TEM sample, you could get all of this information.
Okay. Did you question, I mean, the way you came to do a PhD at some point, did you question the path and say, oh, I should have done engineering to start with instead of going into science? And because you ended up in engineering, that's maybe surprising to many people who know what you have done. So did you question the path you took?
Not really, not too many conscious decisions, but things like I mentioned with the chemistry exam that determined the outcome.
Mm-hmm.
And
yeah. were you maybe just thinking, oh, I shouldn't have done this at the time because you failed an exam, or you just let's move on and carry on?
Yeah, I think so. The latter, just guided by circumstances and doing the best in the present situation.
Yeah. So, but a graduate school, essentially, you went into this knowing you wanted to do research. Is that fair?
I think by that time, yes, science had become an interest, a passion, and doing research was something that I found exciting. Actually, doing research rather than passing exams. So I remember the MSc exam, the last exam I took apart from the PhD oral exam, I gave a sigh of relief at being exempt from these written exams, which have been going on for too long.
Yes. So, but did you feel that when you were younger, before going to university, you wanted to do research, or did you play with things that might have given you a hint you wanted to do research or engineering?
When I was a young child, an aunt of mine gave me a chemistry set.
Okay.
Against advice from my parents. And so I got interested in chemistry and then later in electronics. In Britain after the war, you could go to army surplus shops which sold electronic equipment and even chemical equipment at knockdown prices. And so I used to tinker with chemistry and with electronics. So practical science is what I enjoyed.
Okay. In a way, when I got interested in microscopy, I was an undergraduate and I saw a microscope, and that drew me into electron microscopy. So it's similar in your case. So what made you want to go to graduate school in that case? Was it because you saw the microscope and you wanted to do engineering and there were opportunities, or were you set in doing microscopy at the time?
Well, it seemed to be the done thing to get a PhD if you could do that as part of the career path for scientists. And that's certainly a necessary requirement today.
Okay. And after you finished your PhD, you went into industry. Can you tell us why you chose that path at the time?
Well, I was working on lead telluride, lead sulfide, and a company called Zenith Radio had a research branch in North London, and they were working on the same materials. And I think because of that, more than anything else, I ended up working for Zenith for 3 years. And there we were trying to make a thin film transistor as part of a flat panel display, because the dream was to have a television that would hang on a wall, flat screen TV. And at Zenith in London, we never got anywhere near to that. And so I eventually applied for a postdoc position in Oxford from an advertisement in the New Scientist, which originally I misread. I thought it said scanning electron microscope. I got interested in electron microscopes. It turned out to be an energy selecting electron microscope. And so I went for an interview in Oxford with Mike Whelan, who explained to me what energy selecting microscope was. And he seemed quite amused that somebody from industry would come and work at the university. So I was offered that postdoc appointment and ended up sharing an office with Ian Ray and David Cockayne. And after a couple of years, they were replaced by John Spence and John Titchmarsh. And that was a good time to be doing electron microscopy in Oxford, because, as you know, they had developed many of the diffraction contrast techniques that are used in microscopy to this day.
And so maybe not many people realize you didn't start your activities in energy loss spectroscopy as a graduate student, but as a postdoc. And at the time, I think there were no commercial systems, and you had to start from scratch, I suppose. So what were the challenges at the time in doing energy loss spectroscopy?
Well, I inherited a TEM that had been modified by Peter Turner, donated by AEI company that made TEMs in those days. And it had the magnetic prism, double prism mirror system, so that you could form electron energy loss spectra or energy filtered images. And in principle, the equipment was ready to use and to get scientific results. But in practice, we had all kinds of technical problems. The machine had been moved from one site to another. We had high voltage problems, had to go inside the high voltage tank, which was an oil-filled tank. But in those days, all microscopes came with a circuit diagram that was understandable. And so it was all vacuum tube electronics, but we were able to get it working well enough to do research. And the original intention was to look at plasmon losses to characterize metallic alloys. I started to become more interested in inner shell, ionization edges, and I used some of the equipment that was already there for electron counting, that kind of thing, to characterize materials and try to develop a technique for quantitative elemental analysis.
And just for people who've been working in energy spectroscopy starting just in the last few years, where it takes a fraction of a second to take spectra, I'm just wondering what were the challenges at the time to acquire one single spectrum. Maybe can you put in perspective? I use a serial spectrometer when I started, so that's a long time ago. So how was it? How did you acquire spectra at the time?
Well, most of the spectra, in addition to the images, were acquired on photographic plates. So the plates had to be developed in the darkroom and then scanned on a flatbed densitometer. And that gave you a graph on plain paper or graph paper. And then you read off from the graph paper, the numbers. That was the method. And so it was relatively slow. Exposure times sometimes up to a minute on the photographic plate. And as you know, a photographic plate has a limited dynamic range. And so, yeah, technical problems that don't exist nowadays.
Yes, and did you, when you had to measure areas or counts in an edge, for example, how did you do that? Because when I first started, I had to scan with a digitizer and then extrapolate, calculate areas, and so on. I heard some of the professors at the time. I remember talking to George Wesley at the time. They used to plot then the spectra on graph paper, cut it out, and measure the weight. Did you do that kind of thing?
I never actually did that. I remember counting squares on graph papers.
Yes, so it's a long way.
That was the integration method.
That's right. So did you, given this challenge, did you ever think this is not for you and, this is too difficult and I should move on and do other things? Did you want to go back to industry?
Well, at least once in Oxford, I got discouraged by the technical problems with the instrumentation, and I wanted to transfer to another project in the metallurgy department. But of course, I was being funded through Mike Whelan to work on the energy selecting microscope. And so even though I did participate in this second project, which was a dedicated STEM that they were trying to build there, I continued with the energy selecting microscope, and that did in the end yield useful results after 4 years.
Yeah, so at the time you were a postdoc, did you meet a lot of people? I'm thinking the time I was a postdoc, it was a great time to meet people. And I just wonder how you made connections and friendships at the time that eventually would come to be important for your career. Can you say a little bit about that? I mean, you mentioned David Cockayne, John Spence.
Yes. Colin Humphreys was there as a lecturer, I think. Peter Rez was there as a student, I think Colin's student.
Yep.
Yes, we used to go for lunch on a Friday, and that was a good time to discuss science projects, difficulties, that kind of thing.
So you help each other meet the challenges and move on. Is that fair enough? Your friends were important at the time for overcoming the difficult times?
I think so. The metallurgy department was actually split up into 3 different buildings, but we used to meet in the main building for coffee. And so, yeah, there was opportunities for interaction.
And at the time, I suppose you were postdoc. How long were you postdoc in
4 years.
4 years. So did you at some point think, okay, I need to do something else and decide I can't be postdoc forever? And I think there are lots of people in these situations nowadays, right? It's difficult to find a job right away, or people prefer to keep doing postdoc work. So what were your thoughts at the time?
Well, I actually went to see a careers guidance officer in Oxford, who said, if you want to continue in academia, you should get yourself a faculty job. And so I applied to universities in Australia, Britain, Scotland, Canada, and the one that offered me the job was in Edmonton, Alberta. And so I went to the University of Alberta initially on a trial basis for 1 year, and they made the assistant professorship permanent. And so I ended up staying in Edmonton for the next 10 years, I think. And during that time, I built a spectrometer. The workshop there, you had to build your own equipment, basically. So even though I expected to be doing high resolution microscopy, I didn't really expect to be continuing with EOS, but I was able to build a spectrometer and continue with the instrumentation and the technique development.
So, I mean, just for everybody to understand, what were, the type of instrumentation you had to build when you were young faculty? Did you had a workshop to help you to do that? Did you have to put hands on or have students developing the instruments? Could you buy components of microscope or spectrometer at the time? So people realize a little bit of the challenges compared to nowadays.
Yeah, well, the mechanical things had to be made in the workshop, and there was a good workshop that turned things out high quality in reasonable time. In terms of electronics, of course, you could buy power supplies, although the power supply for the magnet had to be fairly high stability, so it cost a bit more than the average. Photomultiplier tube was used as electron detector. That's a very good detector. That was taken from a jail microscope. And so it was not too difficult, really. We started with serial eels, and by that time, Gatan had started making instruments. So I bought a Gatan serial spectrometer and later a parallel recording spectrometer. But we also did lots of tests on alternative parallel recording schemes using photodiode arrays of various kinds.
So at the time, probably the pressure of publication wasn't as high as it is today. So did you worry about getting papers out? Did you worry about getting a certain number of publications per year? Or how did you work with your students and reassure them then that it's okay, things take time, and if you build your equipment, maybe a couple of years before you get anything done? So how did you cope with those challenges at the time and different pressures?
Yeah, no, I didn't worry too much, and there was less pressure than nowadays. And when I arrived at the U of Alberta, my impression was that it was a privilege to be a university professor, and that the support staff, the administrative staff, were there to make the life of university professors as easy as possible. And so I found it not too difficult. Getting a grant, even though it was a low-level grant compared to today and compared to what you get in the USA, wasn't difficult. The NSERC granting authority made it fairly easy to get started in research. And publications seemed to come fairly naturally.
Okay. And you mentioned that there was a microscope at U of A at the time, or did you have to buy it? And at the time, I think the largest grant, I think it was almost impossible to buy or get a grant for a good microscope at the time. So how did you start up, and did you need to ask for large grants for money for this?
No, we had a GEM 100B 100 kilovolt electron microscope that was the high resolution instrument of its day. And so I was able to use that and add to that. So no problems about the microscope. And getting a few $1,000s, tens of thousands to buy supplementary equipment turned out to be not too difficult. So, and in those days, of course, eels was a specialized area. Not many people were working in it. And so it was a small community, and people helped each other, I think, with ideas.
And so if you had to buy a microscope, you would have had to put people together. You couldn't get a microscope as a startup, for example, at the time, I suppose.
No, there were not large incentives at that time, but I did, after 10 years, leave to go to the United States. I spent 5 years at Stony Brook, which was then part of the State University of New York system. And they had a Philips TEM. And during that time, I actually became department chairman for 2 years, which was an interesting experience. I don't regret that. Never a dull moment. But eventually I decided that I ought to stay with research. And so I ended up going back to the University of Alberta and spending another, 10 years in the same department, essentially in the same position. And the difference between Canada and US, I found quite interesting, because in the US, as you probably know, the emphasis is on more on short-term projects. You can do very well in the US if you work hard and keep up with the literature and basically follow the money. You can build up a large research group of students. Whereas I think the largest number of students I've ever had at the same time is 3. And so in American terms, that's a very small effort. But when I reapplied to the granting agency in Canada, I noticed that one of their statements was that we fund long-term research, which to me was quite a refreshing change from what I saw in the USA. And NSERC have funded my research even up to the present day, even though I've been retired for 15 years. It's been a good support. And in Canada, I think the less pressure it makes for the possibility of doing more long-term research, more basic research, more easily.
Yes. And then what made you, I think things were going well at U of A, at University of Alberta. So what made you just jump and try something, go to a different country, actually, and a different system? Did you think you wanted to try something? Can you explain why you made this diversion to the US for a few years?
Well, I suppose it was the challenge and the fact that funds were available in the US greater than in Canada. And many of the colleagues, David Joy, various people were working in the States, and they encouraged me to join the US enterprise. And it certainly was interesting.
Okay. And in terms of your approach to research, I think it's different. It's much more focused, I think, compared to probably what you see these days. And how can you say something about how you characterize your approach to doing research? You mentioned you had some engineering background, and so how do you characterize the way you do research?
Well, as you know, the kind of research we do in microscopy involves a mixture of different disciplines. So there is certainly some engineering component. And so I think having an interest, a background in engineering probably was a help. Having a limited education in physics probably was not a help, but each person should concentrate on what they do best, I think. And so I tried to make the best use of what abilities I had.
Okay, and you remain very focused. I think it's fair to say you're dedicated your career, mostly of your career, to energy loss spectroscopy, and you wrote a book with different editions, and I think it's been really a major contribution to the field. I think if I look at how I started, I was very fortunate to have got your book. I remember reading it from one side to the end, the beginning to the end, a few times when I started. So what made you decide to write the book? This is a daunting task, and I remember I had to write a chapter in a book, and it was hard enough, but writing an entire book, what made you want to do this? And
well, I think the idea started in Oxford, and the original idea was to write something about core loss microanalysis, but it ended up being much more general than that. I think also John Spence, with whom I shared an office, had the idea of writing a book on high resolution electron microscopy. And so I think for the year before he started in Arizona State University, he made a start on that book. It took me longer to get the book out with Plenum. I think it was 1986, and I'd started in Canada in 1976. But I've had the luxury, I think, of being able to choose what I did in research. And the book actually started when I had a sabbatical year in Cambridge, 1974, possibly. And so I spent time in the new Cavendish lab in the library there, reading up on various things and writing out in pencil on paper, which was the standard method at the time. Started writing a manuscript for the Eels book.
Okay. I remember there was I think a review article you had compiled many different references. I think that might have been the first step towards that. Is that what happened? I don't remember the reference, but you had a review article in the field.
Yeah, well, Eels was a developing technique. There were scientific conferences. Jahari in Chicago organized one series. M&M, EMSA as it was called then, had annual conferences. And there was a community starting to develop. And so review articles, sometimes I was invited to give a talk about eels, and that became a review article.
And how, I mean, to these days, at the time, I think it was difficult in different ways, right? You didn't have the internet to download papers, and so you had to go to the library, make photocopies. How did you keep up with the literature at that time compared to what you can do now? Because the field was, well, there were not a lot of articles in energy loss spectroscopy. Today, there's hundreds of publications, if not more, every year. How did you keep up then and today? What are the challenges? What were the challenges then?
Well, things were certainly less efficient because you had to go to the library, find out what was on the shelves, make photocopies, store those in a filing cabinet, that kind of thing. On the other hand, the field was progressing, but I would say much more slowly, and it was a smaller field. Today, it's difficult. I find it difficult to keep up even with what's happening in eels. And so for that reason, partly I've concentrated on trying to understand radiation damage, which has become a problem of interest to more and more people. As the instruments get better, the problems of damage and basic physics problems start to become limiting. And so I've tried to use my physics background, chemistry background to address those kind of problems.
And overall, what do you think is your one, well, at least in the academic area and maybe the other research, what are the most significant contribution you see of your work?
Well, I think probably the eels book, as people have said that it has been useful in their research. I also wrote a book for undergraduates based on the course that I taught at the University of Alberta. And I think both of those have been reasonably successful. And so I think my contribution maybe is in terms of trying to explain physical principles, engineering principles in a way that is readable. At least that's what I hope.
So you're a very modest and humble person. And I mentioned the impact of the book it had on my academic career, and we know the impact it has done on many different researchers, and how the book really made eels take off, and I think it got a lot of interest. So you're being recognized by many societies, the Microscopy Society of America, the Royal Society of Canada. But at the end, what makes you most proud, I think, in seeing your recognition or the accomplishments when you go to conferences? How do you see this recognition?
Well, it's nice to be invited to conferences to give a talk, but I think the main thing that has pleased me is if people send me an email or come to me at a conference and say that some paper I've written has helped them in their research. That's the kind of feedback that I think is satisfying.
Yes, I remember when I first met you, it was a conference in Canada, University of Guelph. We sat in the student center. I showed you some results, and I still remember just the fact that I was able to talk to you and show some of the results. It turned out I didn't have things right at the time, but I really remember the discussion. And I think, like many other people, it's important to meet distinguished people that are very approachable. And I remember, meeting you, meeting Christian Colliex, meeting Andrei Krivanek at conferences, just something that it's nice to do at conferences. Of course, these days, at the time we have the interview, we are in a pandemic. We have to meet virtually, but I think it's important to see the benefits of meeting people and the impact, long-term impact they have on research. So over the years, what do you think would have been the major changes in the field, that I would say the big milestones in the field of energy loss spectroscopy? How you've noticed, of course, you started with measuring number of squares in graph paper. What would you think is the biggest change or the improvement that you've seen in the years, over the years?
I think electronic instrumentation that has made data recording much easier and more powerful. And as part of that, I think Egerton company has played a large role. They have developed instrumentation in such a way that it can be added to any TEM. In the past, in the Oxford days, we had to design a spectrometer to fit a particular electron microscope. Now you can buy a spectrometer that will fit on any TEM. And that has made an enormous difference. And fast recording makes everything much more possible. So people are doing things today that would have been unthinkable 10, 20 years ago in terms of the amount of data and data extraction.
Yeah, when I started, I remember my graduate work, we were trying to build a EELS imaging system with parallel EELS, PEELS as it used to be called. And we had a parallel spectrometer at the University of, I was fortunate to have access to a CM30 microscope at the time, brand new with a PEELS. And when we talked about acquiring spectrum images, so every pixel, a single spectrum, I remember some people saying, they were laughing at us. Why would you want to do that? It's going to be impossible to store all that data. And here we are today with gigabytes and gigabytes every single spectrum image. So I think the field has evolved so much over the last 10 years that some ideas that were seen as ridiculous at the time are today something that we take for granted. I think that's an important evolution for people to realize. You also think that the way research is being done today is different from what it used to be a couple of decades ago? I can certainly vouch for that, but what are the different pressures that researchers have today and the way that they have to change the way they do research? Do you want to comment on that?
Well, there is obviously more pressure these days to work on practical problems and to work in collaboration with other people in other disciplines. And along with that, universities have become much more businesslike. And so the business model has taken over, and that has, I think, positive and negative effects on scientific research. But certainly it's a different world, more competitive, maybe more productive.
Mm-hmm. And I remember at some point there was this very strong pressure to look at impact factors and publish in high impact papers. I remember you had a strong opinion of that. Do you want to share it?
Well, I've written fairly strongly about the use or abuse of impact factor to characterize journals, to characterize research groups, even universities competing with each other in terms of impact factor. It can have a positive incentive effect, I think, but I think it's now recognized that it can lead to pseudoscience, incorrect evaluation of people, and it acts as a shortcut. It's liked very much by administrators because it gives the administrators a number to characterize each person by. But I think that's no substitute for a mature evaluation of actually knowing the person and what is the significance of their results. And it leads also to this rapid publication syndrome, publishing results as soon as possible without always the reflection that might be desirable.
Yes, I will not quote what you said in that article, but I remember very clearly, and it was refreshing to see established researchers taking a stand on those points, because I think it puts on young academics and students particularly a lot of pressure on doing something quick, as you say, and not necessarily as good, and certainly not as in depth as it used to be. So if you look at your path and how your career evolved, what would be the advice you can give to young research students, or students are doing graduate school at the moment?
Well, I guess it would be to follow your passion, do things that you're interested in, because a large part of your life will be earning money at a job, and it's good that you enjoy the job. The money, of course, is useful, but psychologists have found that more money doesn't necessarily lead to greater happiness. So yes, and I think the university still has advantages as a place to do research, a place of intellectual inquiry. I hope it remains like that.
Yes, and maybe one of the benefits of being in academia or research in general, depending on flexibilities, but it's to be able to meet other people. Do you see other benefits, for example, in being able to go to conferences? What has been your experience in benefiting in terms of your personal development, getting to know different cultures?
Well, the scientific conferences around the world have been of great benefit to me, and I've been to places I would probably never have visited if it weren't for the scientific incentive. And I think we're lucky to be doing science, which is an international language. If you study law or even engineering, you cannot necessarily practice in a different country. They have different rules. But science is an international language, and I think I've benefited from in-person meetings. The last couple of years, of course, have been different, but Zoom and facilities like that, I think, do make it possible. There are certain advantages to having online meetings, and I think in the future, maybe a mixture of personal meetings, online meetings might be the best thing.
Yes, and even if you mentioned that you retired 15 years ago, it sounds like a long time ago, but it went very quickly. I remember the conference we organized to celebrate or mark your retirement. So since then you remain very active. You published landmark papers in the area of electron beam damage. So how do you keep going with your activity? What motivates you to carry on research? You have beautiful mountains close by, and you enjoy travel. So what keeps you really in the field and wanting to carry on?
Well, I think just curiosity about what's happening in the field of electron microscopy, EELs, damage studies. And if I see an area where I think I can make a contribution, then I'm happy to continue. I still have a small research grant, which has paid mainly for travel and occasionally computers. And it just adds to my life. I think it's good to keep active mentally as well as physically.
Yes, and I know you're traveling, well, when it was possible to travel to give lectures. We're fortunate to have had you at the McMaster Summer School coming practically every year. So do you enjoy giving lectures to students? What drives you to do that?
I do enjoy talking with students, and I enjoy lecturing to smaller groups more than large groups. So teaching to 100 students, I didn't find as satisfying as lecturing to a smaller group, or students who have motivation to be there. They're not sitting in the lecture hall because they have to be there. And so, yeah, I've enjoyed that.
Yes, and I know you've been in China giving lectures. You've been in Arizona State. You participate to the winter school. Where are the places you visited that I think were maybe the most interesting places? You would not have gone otherwise.
I went to Hawaii once when there was a conference there organized on diffraction. I think it was John Cowley organized the meeting. Yeah, it's been a pleasure to visit these places and also to meet with people in these various places.
Yes, and how do you relax? Because you're very active in research. You have special activities you want to do when we are off?
Well, here in Canmore, I play table tennis twice a week with the Canmore seniors. There's a remarkably active group of 70s and 80s, people in the 70s and 80s, playing table tennis and other games. I try to do walking in the summer. Canmore is a great place for hiking. Not so keen on winter sports.
Okay. I think we have pictures of you on the mountains. I think so. It's nice to see that. I hope this is showing at this moment. And so I also think you're avid music player. So I remember getting from you once a nice concert. You played the full orchestra. Can you tell us about your music these days?
Well, as a young boy, I had music lessons, piano lessons, but I never used to practice much between lessons, and so I never became a good pianist. But some years ago, I heard a recording by there's a New York jazz musician called Bob James, who had arranged Rameau harpsichord pieces for electronic sounds. And this he'd made into a wonderful CD. And I developed the idea of trying to do the same kind of thing. And there was a PC program called Cakewalk that I purchased, and I bought some sound generators and tried to do the same kind of thing with very unsatisfactory results, I think. But then some years later, Apple came up with a program called GarageBand, which came free with any Macintosh computer. GarageBand is a MIDI sequencer, so it allows you to play any kind of sounds, musical or otherwise, at any particular pitch. You have complete control over the timing, the loudness, and so you can reproduce the sound of a full symphony orchestra or any instrument virtually, because you can buy recorded sounds very cheaply, and even electronic sounds, and mix these and come up with a performance of your own without any training at music school.
Yes, so I received a piece from you a few years ago, and I really love it. I don't know if we will be possible to put the link to that, but I've been impressed. I didn't know you're such a talented musician as well, and it will be interesting for people to know that.
Well, I started off making CDs, and then I got the idea of combining that with video and putting it on YouTube. And the video usually consists just of the musical score, which is probably gobbledygook if you don't read music, but to a musician, this is important. It's what the composer intended. And so I've generated, I think, 40 odd music videos on YouTube. And if you are interested, you can search for Ray Egerton, all one word. And there are some pieces there ranging from George Gershwin to Leos Janáček.
So we'll put those on some links, I'm sure. But I really encourage you to go and listen to them. The sunrise in particular is very impressive. So go that. We meet now people playing tennis, table tennis, and so on. And I just wonder how the interactions are, because I'm sure it will come up in the conversation that you're a scientist. So I just wonder what they think about the fact that you're a scientist. You're, you know, some people think, oh, they know what professors do. And when you tell them you're a scientist, what do they think?
I'm not sure what they think. Some people, when you tell them that you are a physics professor, they retire in horror. Or they say it was their worst subject in high school, or their best subject that they enjoyed the most. So I don't really know. I think university professors are a component of society, a necessary component, but so are many others.
Yeah, so if you have a message for the general public about science, I know it's difficult these days, a lot of controversies, and I will not mention which ones, but what would be the message for the general public about the impact of science and the decisions that are made?
Well, I presume that most people watching this are already scientists, and so they know all about science. My hope is that science can contribute to the good of mankind, and that's not guaranteed. It can be misused as well as used for good purposes. And so I hope that in the future things do develop in a positive way. Climate change is one obvious example of how science can contribute to the betterment rather than the worsening of conditions on Earth.
Yeah, and there are many other examples at
Yes.
this moment during the pandemic, and it's good to hear your view on this. So, Ray, it's been a pleasure to learn a little bit more about you. I've known you since I was a graduate student. I was very fortunate to live in Canada, have you as a neighbor, a scientific mentor. We didn't interact so much scientifically. We didn't publish, I think, papers together, maybe one or two. But so I would say I was very fortunate to interact with you. And I, on behalf of all users of energy loss spectroscopy, people who use everyday energy loss spectroscopy for routine work to the advanced work, I want to convey the appreciation for your contributions in the field. And I want to thank you for making the time to meet with me and sharing your thoughts with the general public. We'll look at this video. So thank you very much, Ray.
Yeah, my pleasure. Thank you, Gianluigi.